class, I want to explain operations on signals. Actually, the signal representation is x of t, we know it. In this representation, this variable t is independent variable. And this variable is dependent variable. Dependent variable. So now you can do operations on independent variable as well as dependent variable. Then what is the purpose of doing some operations on signals? See, we all know signals carry information. Okay, so by doing some operations on the signals, the theme of this operations is to get good information, to get exact information, to get better information. That is the main objective of operations on signals. Okay, so now let us start. Operations on dependent variable. Okay, so what is this dependent and independent? This x always depends on t, but t is independent. It won't depend on any parameter. T is independent. Okay, so now we'll see operations on dependent variable. First operation. Amplitude scaling. Amplitude scaling is the first operation. What is amplitude scaling? So x of t is our original signal. Okay. Then the scale version of x of t, let it be y of t, is nothing but c into x of t. What is this? Scale. Y of t is the scale version of your x of t. And that too, that scaling is for amplitude. Yes. Here the scaling factor is c. C is the scaling factor. Scaling factor. So when this y of t equal to c into x of t, amplitude of x of t gets multiplied by c, or I can say amplitude of x of t gets improved by c. Another important point is when you increase the amplitude of the signal, there is no change in the shape. No change in the shape. Okay. This is for continuous. For the discrete case, you can write it as y of n equal to c into x of n. Okay. What is the device that can perform this amplitude improvement or amplitude scaling? Is nothing but the device that can do amplitude scaling is amplifier. Amplifier can do amplitude scaling. Take one example. Suppose your x of t is like this. Okay, what is the peak to peak amplitude? You all know the amplitude is measured in volts. So the peak to peak amplitude, this is one peak and this is negative peak. The peak to peak amplitude is 2 volts. Okay, now if you want to draw y of t, which is 2 into x of t. Okay, means the amplitude gets multiplied by 2. What is actually the amplitude of x of t? Peak to peak amplitude is 2 volts. When it gets multiplied by 2, it becomes 4. So the signal is like this. And see here, the shape is not changed and this time period is not changed. The time period means the frequency or time period is same. So amplitude scaling means only there exists change in amplitude, not in shape or not in time period or frequency, etc. Suppose x of n is, then want to draw y of n that is 2 into x of n. What is the amplitude for the sample at n equal to 0? Actually it is 2, but if it is multiplied by 2 it becomes 4. 4. At 1 you have the amplitude of 1. So now it becomes 2. Here also it becomes 2. So this is your amplitude scaling. Now we'll see addition. Let x1 of t and x2 of t, x1 of t and x2 of t are two signals. Then the signal y of t obtained by the addition of x1 of t and x2 of t is given by y of t equal to x1 of t plus x2 of t in continuous domain, or in discrete domain y of n equal to x1 of n plus x2 of n. Okay, the device that can perform the addition is called mixer. Mixer can do addition. What is the symbol actually? This is the symbol x1 of t and x2 of t. This mixer can do both addition and subtraction. So just take like this, plus or minus. So the output is x1 of t plus or minus x2 of t. Take one example. This is your x1 of t. This is your x2 of t. Then let me draw x1 of t plus x2 of t. Yes. Now at 0, yes, x1 of t is 1 and x2 of t is 2. So now for the resultant x1 of t plus x2 of t, 1 plus 2, 3 will come first. 3. Next, between 0 and 1, x1 of t is 1. So here it is 2. 1 plus 2 is 3. So between 0 and 1, I'll get 3. Between 1 and 2, x1 of t is 2. And here 1 and 2, between 1 and 2, x2 of t is 1. So 2 plus 1 is 3. Again, between 1 and 2, you have 3. Between 2 and 3, it has 1, it has 2. Again, 1 plus 2 is 3. So it is 3. Okay. So at 3, the two signals are closed 0. So x1 of t plus x2 of t is also 0. So now let me draw x1 of t minus x2 of t. Okay. So at 0, if we see x1 of t is 1, x2 of t is 2. So what is x1 of t minus x2 of t? 1 minus 2. So it is minus 1. So you have negative signal also. Let be minus 1. So at 0, you have minus 1. Next, between 0 and 1, x1 of t is 1 and x2 of t is 2. So 1 minus 2 is minus 1. So between 0 and 1, minus 1 remains. Between 1 and 2, x1 of t is 2 and x2 of t is 1. So 2 minus 1 is 1. So it goes to 1. And it remains at 1. So between 2 and 3, this is 1 and this is 2. So it is 1 minus 2. So it is minus 1. So again it goes to minus 1. It remains. Okay, so now at 3, the 2 are 0, so it is 0. So this is your x1 of t minus x2 of t. For the discrete case, let x1 of n as 1, 3, 2, 1. x2 of n as 1, minus 2, 3, 2. So what is x1 of n plus x2 of n? Yes, 4 samples are there. Before doing it, if you want, you can plot x1 of n and x2 of n. In the form of samples you can plot, but no need actually. Directly you can do this samples addition. So 1 plus 1, 2, 3 minus 2, 3 plus minus 2, 1, 2 plus 3, 5, 1 plus 2, 3. This is x1 of n plus x2 of n. What is x1 of n minus x2 of n? Simply you have to subtract x2 of n samples values from x1 of n. 1 minus 1, 0. 3 minus of minus 2, 5. 2 minus 3, minus 1. 1 minus 2, minus 1. Multiplication. So again, if x1 of t and x2 of t are two signals, then the signal y of t obtained by multiplying x1 of t and x2 of t is written as x1 of t into x2 of t. The device which can do this multiplication is multiplier. So now let me take example. This is your x2 of t. So what is your x1 of t into x2 of t? This is into x2 of t. So between 0 and 1, if you see x1 of t, it has one ramp. Here between 0 and 1, you have one stub type and with amplitude 1. So this 1 into ramp is ramp only. So between 0 and 1, you have ramp of amplitude 1. That be 1 and 2. Okay, between 1 and 2, x1 of t is 1 and x2 of t is 0.5. So 1 into 0.5 is 0.5. So it goes to 0.5. This is 0.5. So between 1 and 2, it remains at 0.5. Between 2 and 3, x1 of t is 0.5 and x2 of t is 2. 2 into 0.5, it is 1. So this goes to 1. So at 3, both are 0. So it is 0. Okay. So this is your multiplication. So let me take one example for discrete also. Let x1 of n as 1, 2, minus 2, 3. x2 of n as 2, 0.5, 1, minus 3. Then y of n. So just multiply. 1 into 2, 2. 2 into 0.5, 1. Minus 2 into 1, minus 2. 3 into minus 3, minus 9. So this is simply the multiplication. But remember, all these operations are performed on dependent variable x. And if you observe all the examples, all the continuous cases waveforms, for the resultant, means for the multiplier, this is the resultant. For the addition, it is x1 of t plus x2 of t. For amplitude scaling, it is c into x of t. In all these waveforms, there is no change in the time t, because these are the operations performed on the dependent variable x. Okay. So now the next operation is differentiation and integration. These are the operations. Suppose y of t is the signal obtained after differentiating the x of t, then that is represented by y of t equal to d by dt of x of t. Suppose if y of t is the signal obtained after integrating the given signal, then that is called y of t equal to integral minus infinity to t x of tau d tau. Okay, so these are differentiation and integration operations. Okay, so totally in the concept of operations on dependent variable, we have seen four. First one is amplitude scaling, the second one is addition, third one is multiplication, and fourth one differentiation and integration. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.